Hello everyone, this is part 2 of Improved Eulers Method. Last time here are the notes from part 1, and we went over the theory behind the concept of averaging the two slopes there, and we came up with the predictor corrector method. And then, as I mentioned on the exam, the next exam, which is designed to be a take-home exam, the way I designed the questions was to include a first part of each where you're using a method that we've used in the past to verify the solution. So for this example, it was the integrating factor, and that's what we left off with last time, was going through verifying the solution by the integrating factor. We had a little bit of excitement here with the integration by parts off to the side, so that was a lot of fun. So now to the actual predictor corrector for the improved Euler method to approximate the solution to this differential equation. If you printed the notes on the third page, I left it blank at the top, but at the very bottom I typed up the tables, so I figured it'd be nice to just have the table to reference rather than like last time I wrote the table out, and that was kind of tedious. So the question is, the differential equation that we're solving is y prime, or you can call it, so this is part B, y prime, you can call it dy dx, but it's our function f of xy, which is y minus x minus 1, and we're given the initial condition that y of 0 is 1. Okay, so you can consider f of xy to be equal to that function, y minus x minus 1. So we'll write out the predictor corrector formulas. The predictor is u sub 1, or u sub n plus 1, and that's given by y sub n. It's really just our Euler formula. Y sub n plus h times f of x sub n, y sub n, and then the corrector. And the corrector gives us our prediction, y sub n for y sub n plus 1, and that is y sub n plus h times, and then this represents the average of the two slopes, so 1/2 of the f of x sub n, y sub n. The first slope, we called it k1 back in our discussion, and then plus f of x sub n plus 1, u sub n plus 1. Okay, so if you look back at the directions in this problem, it says to apply the improved Euler method over the interval from 0 to 0.4 with a step size of 0.1, and then construct a little table with the approximate and the actual solutions at each step. So it looks like we're going to need 4 steps to get to 0.4. So we're going to start, the easiest way to start this to kind of organize the solution is to write out where the first step brings us to in terms of x, and that would be 0.1. Okay, because note that x is 0 here, so basically we're starting at x sub 0 equals 0, because y of 0 is 1. So our first step brings us to 0.1. So the predictor u sub 1 would be the previous y value, so that was the initial value of 1, and then plus the step size, 0.1, times the function, the derivative evaluated at x sub n and y sub n. Now the function, the derivative again is y minus x minus 1, the given y prime, dy dx, whatever you want to call it. No matter what, I always like to put the function in brackets. And we have our y, which is our initial y value of 1, minus our x, which is the initial x value of 0, and then minus this 1 that's part of the formula for y prime, or f of xy. So this extra term actually goes to 0, and u1 is just 1. So then the corrector, y sub 1. Okay, it's going to be y sub n, so that's still this 1, plus the step size point h, but now times 1/2 of, and then we're going to average the two slopes. The first slope is actually just going to be what this slope was, f of x sub n, y sub n, so you can see that's the same thing. So if you want to think about it again, y, which is 1, minus x, which is 0, minus 1, or you could just realize that it's always going to be this previous slope, and then plus, because we're averaging the two. Now, make sure you understand this concept. X sub n plus 1, that's the new x value, so where we step to. So that value of x is 0.1. The y value is going to be replaced by u sub n plus 1. So that was the previous u value. So if you want to make sure you distinguish that y, it's the 1, I'll put little cap and hat on it, or little hat and feet, or whatever you want to call it. So that's that 1 minus the x, which again was the new step to 0.1, and then minus the 1 that's part of the formula. Okay, so then obviously you're going to get a calculator, crunch that down. You should come up with 0.995. Okay, so then we take our next step. So we come up to an x value of 0.2. And the predictor is the previous y value. So now we use our result from the last step, 0.995, and then plus the step size 0.1 times f of x sub n, y sub n, which represents the previous, because we're going to n plus 1. We go to the previous one, so now we're using these, this y value and the x sub 1 value, the y1 and the x1 values, because we're at x2 now. So the formula again, y minus x minus 1, so y 0.995 minus x, that's the previous x value of 0.1, and then minus that 1 is just part of the formula. And so when you crunch all that down, you get 0.9845. Okay, so now the corrector, y sub 2, this should be u sub 2, I'm sorry. Okay, so now the corrector, y sub 2, is going to be y sub n, so that's the same previous y value, 0.995, y sub 1, basically, because we're at 2, so go back to y sub 1, plus the h, still 0.1, times 1/2, part of the average of, okay, now, once again, the first part of this, what's in brackets here, is just the previous function that we evaluated. So you don't really need to think about it again. I mean, if you wanted to, you could say to yourself, okay, it's the previous xy values, so that's the 995 for y and the 0.1 for x. 0.995 minus 0.1 minus 1 was part of the formula. Or once again, you could just look back at this value here, and that's exactly what it's going to be the same. It's never going to change. It's always going to be that way. Okay, but now you have to think about the new x value and the predictor value. So this predictor replaces y. So this 0.9845 that we just found replaces this y in the formula. So 0.9845 is the y, minus the x, which is the new x value, x2 of 0.2, and then minus the 1 that's part of the formula. And that crunches out to be 0.978975. Okay, so now we're up to x3. Just a couple more. So therefore, u sub 3 is going to be the previous y value, 0.978975, plus 0.1 times the function evaluated at the previous x and the previous y value. So again, the function y minus x minus 1, the previous y, that value 0.978975 minus the previous x value was 0.2 minus 1. Okay, so then we crunch all that down and should get 0.9568725. You want to try to carry as many decimals along as you can, because if you cut them short too early, then you definitely get some error due to rounding. So I'm going to carry them along as far as I can. Okay, so then the corrector, y sub 3, is basically y sub 2 again, 0.978975, and then plus the step size of 0.1 times the 1/2, and now the average of the slopes. And once again, the first slope is just the same slope that was used for the predictor. So if you want to think about it again, that's fine. I'm just going to recopy it. And then plus, now we have to think about what the new slope is. And the new slope is the new x value and the predictor value, u sub n plus 1, that we just predicted in place of y. So u sub n plus 1 is this u3 value, the 9568725, minus the x value, which is the new x value of 0.3, and then minus the 1 that again is part of the formula. So then, crunching down all that arithmetic, you get 0.95067375. Okay, and now finally x sub 4. So unfortunately this is as far as we're going to be asked to go here. And so one more time, u sub 4, the predictor. You're going to use y sub n, so the previous y value, 950767375, plus the step size, 0.1. Okay, so we're going back up here to the predictor formula, times the function evaluated at the previous x and the previous y. Okay, so again, the function's y minus x minus 1 previous y, this value, 0.950, $767, $375, minus the previous x is 0.3, and then minus 1, that was part of the formula. So crunching all that down, we get u sub 4 to be 0.915, 844, 1125, and now the corrector, y sub 4. And so y sub 4 is the previous y value, y sub 3, so same value as was used for u sub 4, the 0.950767375, then plus the step size of 0.1 times 1/2, and now the average of the slopes. And again, the first slope is just the same slope here that we used for u sub 4. So I'm just going to recopy that. 950, 767, 375. Minus 0.3, minus 1, and then plus. Okay, now is where we have to be careful. And we're thinking of the new slope, that is the new x value and the y value replaced by the predictor we just found. So u sub n plus 1 was the 915,844. So that's our y value, because we're doing y minus x minus 1 again. So 915,844, 1125. Excuse me. Minus the new x value, 0.4, because it's y minus x, and then minus 1 was part of the formula. Okay, so finally we get y sub 4 is, when you crunch all that down, 909, so 0.909907. No, 909097, I'm sorry. We get 909097, 9494. Okay, so then they ask us to make a table of values, and I did that already just to make sure, as I mentioned when we started this, so we didn't have to recopy. You don't have to stand here and watch me recopy all these numbers. But make sure you understand how to find the exact value, the exact or actual, whatever you want to call it, is found from the solution. The solution, recall, was given and we had proven it. So the actual solution was y of x equaling x plus 2 minus e to the x. Okay, so that was from the given, and that's what we had verified. Recall in part A. And that's what we used to find the actual at each of these x values. So if you wanted y of 0.1, it's just 0.1 plus 2 minus e to the 0.1 power. And you're going to get approximately this 994,829, the first value I have listed in the table. So similarly, if you want y of 0.2, just plug a 0.2 in here for x. So 0.2 plus 2 minus e to the 0.2. Excuse me. I'll just say dot, dot, dot. So you can verify those. So, interesting to see, Eulers' method was a little bit rough. If you look back at the table, there was some, I don't know if you'd call them unacceptable discrepancies, but they weren't really as close as we'd like. But you could see in comparison here with these values, they're pretty close. Not very far off here at all, just to the nearest thousandth, and even up to the step size of 0.4, we're at least to the nearest hundredth, and it's not really far away in the thousandths place. So that shows kind of a nice approximation. So we're going to come back and finish up this unit with one more approximation method, and it's the one that's most widely used, and we'll see you when you're ready.